Superposition of waves means that there are two waves in the same place at the same time. They are overlapping like the pink wave in the blue wave here. In this topic, we'll talk about a few phenomena that occur when two waves are superimposed. The first phenomena is known as interference. When two waves are superimposed, they'll interfere with each other. This means that the magnitudes of the displacements of the waves combine to form the resultant wave. Take a look at this simple example. We have this red pulse moving toward the right and we have this blue pulse moving toward the left. Eventually, they get to the same place at the same time. Now, assuming this is a mechanical wave, the particles of the medium can't be in two places at the same time. So, the displacement of the red pulse and the blue pulse combine to give us the resulting wave. If we call the displacement of the red pulse 1 and the displacement of the blue pulse 2, then the resulting wave, while they are superimposed, would be 3 now. After they interfere with each other, they just continue going the way they were going as if nothing ever happened. Let's take a look at a couple real life examples of this. Here, we have two pulses heading toward each other and right. There they interfere with each other to cause a taller pulse. Same thing here, two pulses with positive displacement heading toward each other, and when they get to the same place at the same time, they will interfere with each other, combining their displacements to create one large pulse, and then they continue on their way. There's a slightly different way that interference can happen as well. Let's take a look at this. Here's a red pulse moving toward the right again and a blue pulse moving toward the left, and now when they get together their displacements are in opposite directions. We still need to combine those displacements to figure out what the resulting wave will look like. So in this case, we could kind of think of the red pulse as having a displacement of like 1 and the blue pulse is having a displacement of positive 2, and those together you get positive 1. So these two pulses kind of cancel each other out a little bit like we saw before, though when they are done interfering they continue moving in the direction they were originally moving with the displacements they originally had as if nothing ever happened. Let's take a look at these couple of real life examples of this trough on the head and the crest of the right had about the same displacement. Interference, you should accept the resultant displacement to be 0. You can see that right here. We have just observed both types of interference. The first type was called constructive interference. This is when the interfering waves have displacements in the same direction. When you can see in this diagram that wave 1 and wave 2 have displacement in the same direction right here. This results in constructive interference. Think of constructive as like building something bigger and bigger. The other type of interference that we saw was destructive interference, and this is when interfering waves have displacement in opposite directions. Take a look over here. Wave 1 has a displacement above the midline. We have as 2 as displacement below the midline, and you can see down there where they are a superposition that they have basically cancelled each other out. Let's take a look at two final examples. Here is constructive interference, and here is destructive interference. One way that we explain whether two waves will constructively or destructively interfere is by talking about their phase difference. This is the difference in degrees of two waves of equal frequency and wavelength. Let's take a look at the sine function and use this as a reference. I use this because hopefully it's something that you are familiar with. So the sine curve kind of looks like a transverse wave. It has a crest and a trough. The crest of a sine wave happens at 90 degrees and the trough of the sine wave happens at 270 degrees. And we are going to use these two numbers of to help us understand phase difference. So here are the two waves, and if I put them literally on top of each other, you won't be able to see that there are two. So imagine that these waves are superimposed. They are in this exact same place at the exact same time. So just like we said a few seconds ago, crests are 90 degrees, troughs are 270 degrees. Same thing for the yellow wave, and if we look at how these line up, we'll see that the crest line up with the crests and the troughs line up with the troughs, and so we would say that there's a phase difference of 0 degrees. 90 minutes, 90 is 0 to 70 minutes, 270 is is 0. The result of a 0 degree phase difference is maximum. Constructive difference. Constructive interference, here are those two waves again, but I have shifted them. We are going to use the same numbers. Through crests are 90 degrees, through troughs of 270 degrees. If we imagine that these two waves were superimposed in the same place at the same time, we would see that troughs and crests line up this time, and so 270 minutes 90 is 180, and 90 minutes 270, well, it's negative 180, but it's still 180 degrees apart, and so a phase difference of 180 degrees is going to result in maximum destructive interference. There are a couple phenomena I want to introduce that can happen when two waves interfere with each other. The first is called the standing wave. This is a pattern of crests and troughs in a medium that appears to remain in one place. This is sometimes described as a stationary wave, and this occurs when two waves of identical wavelength, amplitude, and frequency are traveling in opposite directions through a medium and have become superimposed. Take a look at this animation. The red wave and the blue wave are the two identical waves. The blue wave is traveling to the right, the red wave is traveling to the left. The black wave is standing wave. You can see there are certain points on that wave, those red dots where maximum destructive interference is always happening. It doesn't matter what parts of the red wave in the blue wave are at those points, they always completely destructively interfere with each other. We call these place nodes. In between the nodes, the waves are experiencing varying degrees of constructive interference. Unlike the nodes, which are always maximum destructive interference, you can see that the red and blue wave fluctuate from maximum positive constructive interference to maximum negative constructive interference. This is what causes the pattern of crests and troughs. So, with the red and blue wave are crests, you are going to crest when they are troughs. You get a trough. These areas in between the nodes are called antinodes. If you like making music or listening to music, standing waves are super important. When you disturb the string of a guitar or a violin or a cello or your vocal cords, a standing wave is created. When you blow air into a flute or a tuba or a trombone or whatever, a standing wave is created inside that instrument. When you strike the surface of a percussion instrument, a standing wave is created inside the material of that instrument. To play your instrument, the point is to change the frequency of the standing wave created to get different pitch. The other phenomena that occurs, and this also relates to music, is called beats. Beats are the alternating loudness and softness of a sound wave due to the interference that happening here. An example: the loud part is caused by constructive interference, and the soft part, the quiet part, is caused by destructive interference. Here's a visual example. There's a green wave and this pink wave look pretty similar, but if we overlap them, we can see that their wavelengths, their frequencies are slightly different at these places. The two waves would interfere constructively, causing the louder part of the sound at these places. The waves would interfere destructively, causing the quieter part of the sound. There's a very simple equation that goes along with beats, and that is the equation to figure out the beat frequency, how many times per second the sound fluctuates from loud to quiet. And here it is the frequency of the beat is simply the absolute value of the difference between the frequency of the two waves. So, for instance, if we had one wave that had a frequency of 220 Hz and another wave of that in a frequency of 223 Hz, the frequency of the beat would be 3 Hz. That means 3 times every second we would hear the sound fluctuate between loud and quiet. Listen. Let's look at another example. We'll start with the same 220 Hz frequency, but now we'll combine that with the 240 Hz frequency. This means that the beat frequency is going to be 20 Hz 20 times every second. It should fluctuate between loud and quiet. This is going to be hard to hear and probably impossible to count. I think you can still tell those fluctuating between loud and quiet. One final example again, the 220 Hz now. Let's combine that with 440 Hz for the musicians out there. These two frequencies are an octave apart. When you double the frequency, you go up an octave anyway. The beat frequency here would be 220 Hz. This probably won't sound like a fluctuation between loud and quiet. It will kind of just sound like one continuous noise.